Thank you very much. Thanks for the great invitation. So since this is a talk on social networks, I would like to start with a social picture. And the social picture is November 1999. It's a family picture. So Boris, myself, and my daughter on the right. Beautiful day. Valferré, Italy. You can see Mont Blanc there. And it was very cold, but of course Boris is very robust. And also, clear skies, and I still have great memories of that trip. So Boris has been an amazing source of inspiration for me for so many years at various stages of my professional and scientific life. And I really enjoyed all the wonderful conversations and discussions, technical and also related to human life, that we carried on over the years. So thank you very much, Boris. It has been a great pleasure to collaborate with you, and I'm looking forward to future collaborations. And of course, happy birthday. So today I'm going to discuss opinion dynamics in social networks. And this is a topic that is not related to Boris' research. Nevertheless, I decided to talk about this for two reasons. The first reason is because Boris is a scientifically very curious person. So if he gets interested in this topic, I'm sure that he can contribute significantly. The second reason is because I was invited to give a couple of talks at the summer school in Moscow last year. And at that time, I already was working on opinion dynamics in social network. But at that time, I started working on the specific results that I'm presenting today. And again, thanks to Boris, because he has been behind the scene of these research activities. So this is joint work with Sergei Persegov, Anton Proskurnikov, they are both here, and Noah Friedkin, who is a professor of sociology from UC Santa Barbara. So let me just give a few motivations on why we are interested in this topic. So we are dealing with networks of interpersonal influences, and you can think about a graph representing the interpersonal influences. So there are individuals who are the nodes, and then it's a directed graph, and then there are connections between the individuals. For example, the opinion of this person is influencing the opinion of that person because there is a directed link. So so the point is that individuals, us, are within a room, or they could be on the web, for example. So individuals discuss a certain topic based on interpersonal influences. So based on discussions, we try to exchange ideas, and we are interested to study how opinions evolve over time. So the first question that we are posing is that how opinions evolve over time. And then there are a number of questions which are interesting from the, philosophical or sociological viewpoint, but I think they're also very interesting, at least from my perspective, from the control and the mathematical viewpoint. So the first question is, do opinions converge at some point, or do opinions fluctuate? The second question is that, do opinions aggregate into clusters, or they don't? Do we reach a consensus of opinion? So all of us converge on the same opinion about a certain topic, or do we find a disagreement? And during the conclusion at the end of my talk, I'm sort of going back to this point here. So there is a model, which is a mathematical model, which was introduced by Friedkin and Johnsen many years ago, and I would like to discuss it for a few minutes. This model is getting more and more attention in the control community. Nevertheless, it's sort of surprising that some of the profound questions regarding stability, convergence, and so on of this model are still largely unexplored. And so that's why it's interesting from our viewpoint. So basically, the point is that we have n agents, and each agent's opinion is a scalar value. So we have x, which is a vector of opinions, which is into Rn. And then we have a discrete time model of opinions, which is represented as follows. So x is the belief of opinion, which evolve over time. It's discrete time. So k is between 1, 2, up to infinity. And then, so this is the belief or opinion. And u is the so-called prejudices. So the prejudices is the a priori opinion that we have about a certain topic before we start discussing the topic. So this is the prejudices. And notice that in this model we set the initial conditions equal to the prejudices. And then we are interested in seeing how this model evolves. There are, of course, a couple of matrices. It's a linear system, so it's very simple. Nevertheless, there are a couple of matrices, so there is a specific structure which enters into the picture. So there are two matrices, which are the matrix W, which is, of course, a non-negative matrix in the sense that all the entries are non-negative. But we are going to make an additional assumption about W in a second. So W is a matrix which represents the interpersonal influences between agents. And then there is a second matrix, which is also a non-negative matrix, which is in particular it's a diagonal matrix, which represents the sensitivity to opinion of other agents. As you can see, here we are dealing with the product of lambda and W. So basically, lambda plays the role of weights. Little more about this model. Clearly, this model consists of two parts. The endogenous part, which shows how the opinions evolve based on the opinion of the previous step, and the exogenous opinion, which is based on the prejudices. As I said, W represents the interpersonal influences, and lambda, the sensitivity to opinion of other agents. Couple of assumptions, very reasonable. The first assumption is that we are doing averaging. So the opinion at time k plus 1 is sort of the average opinion at time k. And so if you see that immediately, you notice that W is a row stochastic matrix. So mathematically, 1 is the vector of all ones. So W times 1 is equal to 1. So it's a row stochastic matrix. And then lambda, the sensitivity matrix, is a diagonal matrix, which is a diagonal sensitivity matrix, which is a non-negative matrix, and it's bounded by 1. So all the elements on the diagonal are between 0 and 1. Quite often in sociology, there is a coupling assumption which is made, and the coupling assumption is the assumption between the sensitivity and interpersonal influences. So lambda is actually taken to be equal to the identity matrix minus the diagonal of W. The reason why this coupling assumption is made is twofold. First, to simplify some mathematics. But this assumption is not really needed. But anyway, the mathematics simplifies a bit. Second, the second reason is perhaps even more important. From the sociological viewpoint, this simplifies the life of sociologists who are actually need to perform experiments in order to estimate W and lambda. So if they set this coupling assumption, they only need to estimate W. Well, here is an example, and then I'm going to iterate on this example in a few minutes. So it's a Friedkin and Johnsen example, comes from the original paper of Friedkin and Johnsen. So we have 4 agents, and these are the prejudices. So agent number 1 starts with an a priori opinion which is 25, the agent 2 is 25, the third one is 75, and the fourth one is equal to 85. And this is, you can verify immediately that this matrix is row stochastic matrix. And please notice this element 1, which is going to create some little problems in a minute. And here in this example, we take coupling between sensitivity and strength of interactions. And so we take lambda equal to identity minus diagonal of lambda of W, and immediately you see that you get this lambda matrix. And in this case, the third entry corresponding to the third agent is equal to 0. And we're going to discuss that in a minute. Okay, so clearly we all know linear systems. So we can write the so-called opinion profile. So the opinion profile describes how the opinion at time k depends on the prejudices. Okay, so it's very easy to do that, obviously. So the question is that, do the opinions converge to a stationary value for k sufficiently large? So do we have convergence? And in order to do that, let's first define rigorously convergence. So convergence, we say that the Friedkin and Johnsen model is convergent if the opinion have a limit for k going to infinity. So which means that we call it XOPD, the opinions, which are the opinion for the limiting value. And this implies that if you just think about the Friedkin-Johnsen model, for sufficiently large k, we have XOPD equal to lambda W, XOPD plus 1 minus lambda U, for any prejudices U. Okay? This is, I think it's very obvious definition of convergence. Well, here, I can immediately state a sufficient condition for convergence, and the sufficient condition for convergence is that the matrix lambda W is sure stable. If the matrix lambda W is sure stable, then the opinion converges to the unique stationary point. So we have a stationary point. And so this is a sufficient condition. It's very easy to verify this formulae, because you have just, you put this on the left-hand side, and then you form I minus lambda W. So if this is sure stable, then this matrix is full rank, so you can take the inverse, and this is exactly the opinion, the final opinion that we have. So if we know what is lambda, what is W, and we know what are the prejudices, we just do these simple matter computations, and then we compute the final opinion. I'm not very happy about this result for the reason that it's only a sufficient condition. So we want to get more. So we want to get necessary and sufficient condition. And this is something that Sergei, Anton, and myself and Friedkin worked on. In order to do that, we need to introduce a definition, which is the definition of stubbornness. So relates, of course, to stubborn agents. And of course, there are in this room many great examples of stubbornness. So the agent I is stubborn if the element lambda II, so the ith diagonal element, is strictly less than 1. So this is a stubborn agent. So it's an agent that is not really listening to the opinion of other agents. Then even more, an agent I is totally stubborn if lambda II is equal to 0. Okay? So totally stubborn. And then we say that an agent I is implicitly stubborn if it is stubborn or is influenced by at least a stubborn agent. And here you can think about this one in terms of a graph. And here there is an agent J, which is a stubborn agent. And this stubborn agent is influencing the opinion of the agent I. So there is a direct link between J and I. So in this case, the agent I is influenced by at least a stubborn agent. In this case, it's influenced by 1. Okay? Just in terms of definitions and terminology, agents that are not implicitly stubborn are called oblivious agents. Okay. By the way, just very quick comment. This is for the non-degenerate case. There are some little technicalities that should be taken care of that we took care in the paper, but here it's just a slightly simplified to avoid some non-triviality condition regarding the so-called degenerate case. Okay. And then here we have a theorem which tells us everything in terms of stability and convergence. So we can say that the Friedkin Johnsen model is sure stable if and only if there are no oblivious agents. So the comment here is that the presence of oblivious agents is the only reason for instability of the Friedkin Johnsen model. Now, regarding convergence, there is a second statement in the theorem which tells us that the Friedkin Johnsen model is convergent if and only if the matrix lambda W is regular, which means that there is a limit for this matrix. Okay, so for convergence, we can conclude that regularity is the only condition that is needed for convergence. I'm going to show an example which clarifies this in a couple of minutes. But before doing that, I want to make some comments with the celebrated de Groot model, which has been used by many people in the control community, people working on consensus. Okay, so the first comment is that I'm talking here about uncoupled sensitivity and interpersonal influences. So the matrix lambda and the matrix W are uncoupled. So we don't take this coupling condition. So the de Groot model, which is a model considered for opinion pooling, is a simple model, discrete time, like as follows. X of k plus 1 equal to W x of k, and the matrix W is row stochastic. Well, the Friedkin Johnsen model is actually a generalization of the Groot model. If you take in the Friedkin Johnsen model lambda equal to identity, immediately you get this de Groot model. Now, a couple of interesting comments. The first comment is that this model is never stable. So it's not stable in the sense of sure stability. Nevertheless, it converges to a consensus of opinion if the matrix is primitive. So primitive means, I'm sure that all of you know this, but it's positive for some m. Okay? So in this case, there is a clear distinction between stability and convergence. So in the case of the group. And the same difference applies to the generalization of the group, which is the Friedkin-Johnsen. So convergence of the de Groot model is necessary and sufficient for regularity and for convergence of the Friedkin-Johnsen model. So to illustrate a little more about these differences, let me actually work on this simple example by Friedkin-Johnsen. As I mentioned, there are 4 individuals. And as you can see, here we take this coupling condition for simplicity. And then we form this matrix lambda. Now, stubbornness is a property of the matrix W. So if you look at this, all the elements in the lambda matrix are strictly less than 1. So all the agents are stubborn. But the agent number 3 is actually totally stubborn because it has a value equal to 0. So all the agents are stubborn, agent 3 is totally stubborn, there are no oblivious agents. So we can apply the conditions, necessary and sufficient conditions for stability, and then we conclude that the Friedkin-Johnsen model is sure stable. Even more, it is convergence to a unique stationary point, and this unique stationary point can be computed with this formula that I've shown a few minutes ago. So we can simply run a MATLAB code and then compute the final opinions, which are given by these final values. So 60, 60, 75, and 75. So let me show a plot showing that how the opinions converge over time. If you do that, you can see that the totally stubborn agent is the red agent, which starts with an opinion which is 75. This person has the same opinion forever. So his opinion is not influenced by the opinion of others. Nevertheless, the others are influenced by his opinion. And what it means that the agent number, so the blue one, starts with a value which is 85, so it's the agent number 4. This agent is stubborn, but is not totally stubborn. So for a while, is somewhat convinced by the stubbornness of this guy that this topic is not that important, so he's sort of decreasing his opinion, and then it's increasing again, and then finally they converge to the same value. So in other words, agent 3 and agent 4, they have different prejudices, but eventually they will converge to the same final value. And this is one cluster. Now, if you look at the other cluster of the other 2 agents, they start with the same value. They have a slight disagreement here, but nevertheless, they converge to the same value eventually. So it means that there are 2 distinct opinion clusters which are formed. And from this case, immediately we conclude that global consensus is not achieved. We don't have global consensus. We have clustering. And this is a key fundamental difference with the de Groot model. So if we run simulations for the de Groot model for exactly the same numerical values, you can see that here there is this stubborn person who keeps the same opinion forever. This one is somewhat converging here. The other 2 guys are actually influenced by this totally stubborn guy, and convergence is achieved. So what is the conclusion here? The conclusion is that the opinions of all the individuals converge to the totally stubborn agent, and so we reach consensus. So this is a key difference between consensus and disagreement expressed by the Friedkin and Johnsen model. Now, one limitation, so this is thanks to Sergei, who came out with the first initial idea during the summer school last year, is that the Friedkin-Johnsen model is a univariate model. So there are n agents which are only discussing one single topic. And so the idea is that what about if we extend this to a multidimensional model where we have n agents and m opinions? And this is what we have done. So the Friedkin-Johnsen model is univariate. So we have n agents discussing one single topic. So the idea now, we have a multidimensional extension. So we have n agents which are discussing m issues. So x1, x2, xn, n agents. Each xi in the classical Friedkin-Johnsen model is a scalar value. Here, each xi is actually a vector, a real vector of dimension m, because we are discussing m issues. And then what we are doing from the linear system viewpoint, we are basically forming an output. So instead of just a state equation, we also have an output equation. So we basically introduce an output, which is y, which we call it the impact. And the impact, the relation between, so the C matrix, the output matrix, between the impact and the state, the Z matrix C, is called multi-issue dependent structure. And thanks to Anton, who actually invented this term, and Friedkin liked it. So, of course, here we also need to play with average opinions. And so the matrix C is rho stochastic again. And now, I mean, we can work on multidimensional version of the Friedkin Johnsen. Here there are two interdependent issues, say fish and salmon. And so, for example, if you look at the agent number 3, again, stubbornness is a property not of the prejudices, is a property of the lambda matrix W, of the lambda matrix or the matrix W. So, I mean, this is a stubborn person. He was a stubborn person in the original model. He's still a stubborn person in this model. Actually, totally stubborn, and the other 3 guys are still stubborn. Now, there are 2 interdependent issues. So, the a priori opinions, the prejudices of the third agent is that 75. So, this person has a very strong liking for fish. Nevertheless, this person has a very negative opinion about salmon. So, a very negative opinion. So, minus 50 in this case, because opinions can be also negative. So, and then we have with this MIDS matrix C, which is rho stochastic for the reasons that I expressed. So, it's this matrix C is given by this value. So, there is a strong correlation to the diagonal, but there are also non-diagonal elements. Okay. And so we can actually stack everything together into a big vector. So X, we call it X, which is simply X1 transpose, Xn transpose, then we take the transpose. So we have this very long vector X. So we do a vectorization operation. And then we can do the same for the prejudices. So we have one U1 transpose, Un transpose, pick the transpose, and then we have a U. And then we simply form a multidimensional model opinions using Kronecker products, which is, you know, very, at this point, it's very intuitive as an extension of the Friedkin Johnsen model, because now, in the original one, we have lambda W, and now we have lambda W Kronecker C. And we have the similar one here. Just for simplicity, here we put the matrix I, but nevertheless, if we want, we can extend and put another matrix here, D. And so it's the same story. And then, of course, we can ask the same questions. Do we have convergence? Do we have stability? And then here we are just 2 quick theorems. The first quick theorem, which is basically no oblivious agents. So if C is rho stochastic, which is this output matrix is rho stochastic, then stability of this multidimensional model is equivalent to the stability of the original model. So basically there is just this additional assumption about C, which is very natural, of course. The theorem 2 about convergence, if some agents on the other hand are oblivious, then we also need to assume regularity of C, in addition to regularity of the matrix lambda W. So we also need regularity of C for convergence. So this is addition. So from this point of view, we have necessary and sufficient condition for the multidimensional model for both stability as well as convergence. Now, there is a problem which actually was posed by us to Friedkin, and we have been able to solve, which is in empirical experiments is actually difficult to estimate. It may be difficult to estimate the matrix C. So the question is that suppose that we know the matrix W, and we know that. Suppose that we know the sensitivity matrix lambda. If we don't, then we form this coupling condition. Suppose that we know the prejudices, and suppose that we have a target final opinion, X infinity. Okay? The question is that, can we estimate the MIDS matrix C? Well, in fact, we can form an optimization problem. And so given lambda, W, X infinity, and U, we can simply solve this optimization problem with somewhat measuring the distance between this quantity here, which is related to the target of final opinion, and the prejudices. Here, this is another identity matrix. I just wrote IMN because it's a different dimension than this I matrix. Subject to C is rho stochastic. And then you can take different norms and use the tools that Steve was discussing yesterday. So for L2, this is a convex quadratic program. for L1 and L infinity, this is a linear program, and then you can solve them. And here it's, again, a simple example. This is the usual W, the usual lambda. We have this coupling condition. These are the prejudices, which are exactly the same as before. And this is the target opinion. And then, in this case, we take a Euclidean norm. So we have a QP program, and then we can simply compute the MIDS matrix, which represents the coupling. Now, please observe that this matrix is row stochastic matrix, so everything works well. So, because when we solve this optimization problem, it's subject to the fact that the matrix C is row stochastic. Well, here there are some plots which are actually interesting, I think. So we have these prejudices. So let's look at the case of independent issues. So we take C equal to identity. This is what we have seen before. And here, this is for the other 4 opinions on different topics. And you can see that in this case, it's interesting because this stubborn guy is not really influencing the opinion over the others. And here, Friedkin likes this because the opinions are basically always negative. Now, on the other hand, things are quite different if we have these interdependent issues, matrix C. Because in this case, this guy is neglecting the opinion of the totally stubborn agent. And here, the discrepancy between the opinion of this totally stubborn agent and the other stubborn agent becomes larger. Now, what is getting even more interesting is that if you run the same simulation for the de Groot model. Now, for the de Groot model, as we had discussed before, we have convergence to here, to one cluster. And here we also have, of course, convergence to the stubborn guy, in the case of independent issues. In the case of interdependent issues, things become completely different. Of course, we have convergence because we have consensus, so everyone agrees on this final topic. But here the concept of totally stubborn person actually changes dramatically because the 2 red stubborn persons are actually influencing each other. So here basically we lose the concept of totally stubborn person. So I'm getting close to the end. Just to motivate a little bit at the beginning of the talk, in the talk there were the 2 words, randomization and gossiping. And so far I didn't talk at all about randomization and gossiping. So where randomization and gossiping comes into the picture. Let me go back to a sentence by Friedkin and Johnsen in the original paper, which has been quite inspiring to me. And the important point is that interpersonal influence do not occur in the simultaneous way. So in other words, if all of us are discussing a certain topic, then we don't discuss that simultaneously because it's impossible to carry on 60 discussions between 60 people at the same time. So, and in fact, it's interesting also because the communications between humans are becoming increasingly asynchronous. So example of asynchronous communications is text-based messages, email, bulletin boards, blog, forum, and so on. These are delivered by our modern technological tools and are independent of time and place. And examples of synchronous communications, phone, conference calls, and so on, and these require humans to decide a common time. So it's much more difficult, to carry on synchronous discussions, synchronous communications between individuals. So this is asynchronous. And so more and more, also using the modern technological tools, we are moving from synchronous to asynchronous. And here, you can think about these comments in terms of a graph. So we have asynchronous models where all the agents exchange simultaneous information through links. And this is, not really realistic, both from the computational viewpoint, but also from the sociological viewpoint. On the other hand, we can think about an asynchronous model which is based on randomization and gossiping. So it means that at time k, you pick one specific individual, and myself, I'm talking to Bob, for example. And this is made at time k. So at time k, only Bob and myself are talking about, and then at time k plus 1, then Bob talks to Costantino, and so on. Of course, if we work with this randomization and gossiping, so randomization is because it's picked at random, and gossiping is because you want to talk to the individuals who are close to you. And so you need to establish some ergodicity properties of this protocol, which was done in a paper by Chiara Ravazzi, Paolo Frasca, Hideaki Ishii, and myself, which came out in in the transactions on control network systems, and we have a subsequent paper coming out in European Journal of Control. So, ergodicity properties, in fact, we extended this to the multidimensional model, and basically, assuming that there are no previous agents, time average, random, gossip-based opinion are almost sure ergodic. Time average is necessary, so Boris is really an expert on that. So time average is actually needed in order to show these almost sure ergodic properties. The drawback is that we slow down convergence, but this is different matter. Conclusions. Very simple conclusions. From consensus to disagreement. The model that has been celebrated a lot into the control community, the de Groot model, which actually was sort of motivation for so many people working on, explains quite well the behavior, for example, of machines, because you have robots or UAVs or so on, and they want to converge to a target. Or maybe animals, you know, you have fish or birds, and they want to reach a consensus, they have a formation and so on. When you talk about humans, the situation is actually quite different, because humans generally don't reach a consensus, and there is a disagreement, and this is what we have to work on. And I believe that we are just at the beginning of the story. So thanks for your attention. Bob.
So you didn't mention much about the graph, like whether every node is reachable from every other node, whether pieces are disconnected.
Absolutely. You can actually, I mean, of course, you know, all these conditions can be stated in terms of matrices, or can be stated in terms of graph.
Yeah.
I mean, if you want to have a sufficient condition for for stability of the Friedkin Johnsen model, the graph should be strongly connected. So if the graph is strongly connected, then the Friedkin Johnsen model is sure stable. This is only sufficient condition.
Yeah.
Exactly.
The second question I had.
But you can state also, you know, of course, there is, because the graph is adapting to the matrix. So basically.
Yeah, and the second question, maybe just to understand the model, but when you do the uptake from k to k plus 1, even if I'm heavily influenced by my neighbors, my prejudice stays as a constant input. That's kind of a bit weird.
In fact, this is I think it's an excellent question, more for sociologists than for engineers. But it's yes, because the prejudice is what they have a priori before we start discussing a certain topic.
But after you influence, yes, my prejudice might go away.
Then you talk. Then I mean, what you are basically, I mean, from the linear system viewpoint, the prejudice is constant, so it's not a function of time.
Yeah.
What you're talking about is basically what is called influence vector. And so you can form another model where you have an influence vector, and then you can study different properties for the influence vector. But it's done on purpose, so they call it prejudice, so it's taken constant, it's actually set equal to the initial conditions.
Other question? Let us thank again.